Well, welcome to the next lecture of basic modeling of biological networks. We are still in chapter 3, so the previous week we've looked at robustness, and this week we will look at fault change detection, but also kinetic proofreading and two-component robustness of two-component signaling networks. So the kinetic proofreading lecture I will record independently of this one, and also the one about robustness of two-component signaling. So this week we'll have, week 4 in fact, so coming week we'll have 3 lectures associated with it. Okay, so a fault change detection is quite a remarkable property of sensory systems, and let me explain you what is meant by this. Okay, so let's imagine that you are standing in a room and over time we are monitoring a certain conversation. Okay, and there is some background, so here, let's say here you have volume. Yeah, and there is background volume. Okay, so there is noise, so maybe there are cars driving by or people speaking in the background. And on top of that, there is a conversation. Okay, so first of all, for us to be able to distinguish this, of course, the volume of the conversation will be, needs to be a bit higher, right? And what we observe, so what we sense with our ears, is the sum of both. Okay, so that is yet going to be higher. Okay. And so to decode the conversation, this means that the key syllables, the key words being expressed by the speaker, can be distinguished from the background noise, this, by just simply looking at the thing, what we have obtained, what we have sensed with our ears. This is the sum of the two signals. Okay, so apparently, so let's say we were able to listen to this conversation despite the noise, so somehow this noise in the background we could filter out. That is already an interesting property of our ears. Of our ears themselves, but there is also another aspect. So if we would do this, have this conversation, but all the volumes would be twice as high, okay, so everything would be, say, here, and we would still be able to distinguish it, that would mean that our sensory system is insensitive to the background noise. That means what it is, in fact, what it's doing is it is each time taking a difference between the meaningful noise and the background noise, and the meaningful noise, of course, are the signals that we speak. So it is somehow capable of correcting for this the baseline noise, even though at all volumes of this baseline noise, just as long as the person who speaks also speaks up when there is more background noise. Okay, so that means we can do noise correction, we can do baseline correction. So in fact that means, so if we can do this type of baseline correction, what does that mean? Well, that means the following. So let me now take the example of the biological network. So let's say we have a signal X, and that is some molecule concentration that we consider fixed, and this signal activates another reaction, activates a reaction that synthesizes another molecule Y, and Y is also broken down. Y inhibits the synthesis of Z, and Z is also broken down, and the synthesis of Z is also activated by X. Okay, so let's say this is our signal, yeah, So in our case that would be green, right? So the total noise plus conversation that we sense. And there is also a response variable, and that's going to be Z. Okay, and we would like this network to have the same feature as our ears and eyes have. So that is that to be able to distinguish meaningful information from background noise by somehow correcting for it. Okay. So what are we going to do? We're going to change the concentration of X, say from 1 to 2 to 4. Okay, so we change it each time with a factor of 2. Then we change it twice with a factor of 4. So 4-fold. So 4, 16, 64. And then we keep it constant for a while again, and then we reduce it by, we multiply it by a factor of 0.5, and then we multiply it by a factor of 0.25. Okay, so we go to 32, etc. Okay, and so that is going to be the time profile of X, and now we're going to look at what the response of Y will be. Okay, so this is X's function of time. What will the system do? Well, the response of Y is independent of Z, it only senses X. So whenever there's more X, you will synthesize more Y. And that means the Y concentration, of course, goes up. And when it goes up, it also will be degraded more. But generally, at steady state, we will get a higher concentration of Y. So if we mark the time points at which we make changes in X, we can try to sketch what we would expect for the dynamics of Y. Well, first, X goes up 2 times, 2-fold. So the expectation is that Y would increase twice, 2-fold, and then it increases more. And then we reduce it by half. Oops. 2 times. That will probably actually go like this. 2 times and then 4 times. Okay. So this is roughly a 1/4, 1/4, 1/2, 1/2. So half-fold response and 1/4 response, a 4-fold increase, a 4-fold increase, and a 2-fold increase. Okay. So what we would expect is that Y would track essentially the values, the steady state of Y would track the input values of X. Now, what happens to Z is a little bit more complicated to deduce, because Z is not only influenced by X. So if the influence of Y wouldn't be there, of course the response of Z with respect to X would be the same as that of Y, because they would both depend in a similar way on X, and the response of Z would mimic that, would mimic the response of Y. But due to this negative feedback loop, right, so these were, I should say, feed-forward loop, this negative feed-forward loop, there is a second effect. So first of all, when Y is activated, X is activated Z is activated at the same time, right? So there's first activation of Y and Z by X on the same time scale. But then when Y increases, the synthesis of Z goes down, but Y continues to increase. Okay? So this suggests that Z first goes up, almost in sync with increases of Y, and then when Y becomes high enough, Z goes down. So a time response of Z will be something like a peak. Okay? But how it will return to the basal level, or whether it will be returned to the basal level, depends on whether the system shows perfect adaptation, so whether actually the steady state level of Z is robust with respect to the value of X. But what we're going to look at is some somewhat weird response, is that the response of Z will always be the same when it is confronted with the same fold change. Okay, so here you have 2-fold increases in X, here you have 4-fold increases in X, here you have half-fold increases in X, and 1/4 fold increases in X. Okay? So, and the idea now is that these responses are identical. But if these are identical, then the basal level of X doesn't matter for the response of Z. It is only the fold change in X that matters for the response in Z. So Z always responds to changes in X, but the absolute level, so whether the starting value of X was 1, 2, 4, 16 or 64, that doesn't matter. The time-dependent response of Z only depends on the number that corresponds to the fold change in X. So if you think of the basal level as the starting level, right, so that is X start, and we call that X0, and the new value we call X, then X0 divided by X is the fold change in X, right? And apparently Z responds to the fold change in X. So Z responds to the fold change in X. And that is sort of what our sensory systems also do, right? So whenever I speak in the presence of background noise, then my volume will increase. So if my volume increases with the same factor as the background noise, then you will still be capable of hearing me, because you can distinguish my voice from the background signal. And then your response is the same when you hear me at a high background noise level, because then I speak up, when compared to the situation of a low background level when I don't have to speak up. So apparently what we do when we converse with each other, when we speak with each other, is we try to keep this difference in volume almost constant. And because I don't need to speak up more, because you can already distinguish my voice from the background noise. Okay, so this fold change detection is a property of your eyes, because you can distinguish me from background in a situation with a lot of light, but also with less light. So in fact, your sensory systems are sensing contrast, and your ears do it. And there are also many molecular systems that do it. So for instance, chemotaxis have been shown to do it, but also epidermal growth factor signaling, so MAP kinase signaling, has been shown to do this. And this particular network, shown here, has this fold change detection property too. And that was first discovered by Uri Long and some researchers at the time working in his lab, and they made a sort of a mini model of this behavior. So let's write down this model. So we have a variable y, and we have a variable z, and x we keep fixed, right, because this is underlined, and so the model they made looked like this. Let me check whether I have the betas not swapped with the alphas. No. Okay. So I know that this is a slightly unusual naming for us, because typically these alphas and betas we could call k's, but they call them alphas and betas. So I decided to keep to have the same symbols. So if you would compare my the chapter of the syllabus to their original research paper, it would be identical. Okay, so fault change detection. We want to prove. We need to prove first the robustness, because every time Z will go back to the same state, basal states, regardless of the value of X. So we need to prove that the steady state concentration of Z is robust, perfectly robust with respect to X. That's what we have to show. And we have to show that Z is detecting fault changes in X. Okay, so those are the two things that we need to show. So let's start with the easy task. That's to show that the steady state concentration of Z is perfectly robust with respect to the value of X. So you know how to do that. You look at the steady state equation. So you said, okay, so steady state 0 equals beta 1 X minus alpha steady state Y. 0 equals 2x y steady state alpha 2. This gives us the steady state concentration like this. And this gives us as the steady state concentration of Z. This is the first equation that we get, but then you see that the steady state concentration of Z still depends on the steady state concentration of Y, so we have to substitute that equation in. Looks like this. So, and this we can rewrite. So first of all, you see that X disappears. And then you see that you are left with this equation. So the steady state concentration of Z, when we express it in terms of parameters only, we see that it doesn't depend on X. So it is independent of X. So ZS is robust with respect to X. Okay, and that's the thing we wanted to show, and indeed that's the case. Okay, and so that's one feature that this network has. It has robustness in it, but that's not the important feature. At least that's not the key feature of the network. So now what we have to do is we have to think how we can prove that this system is, that Z is detecting fault changes in X. Okay. So what does that mean? That means that the changes in the concentration of Z are always the same when the same fault change in X has been applied. So again, Z is fault change detecting. Z is detecting fault changes in X if, for the same fault change, the response of Z as function of time is always the same. So that must mean that we should be able to write this set of equations in terms of fault changes. Because if this system is fault changing, is detecting fault changes, and this system of equations gives us the dynamics of z, right, then we should be able to write this system of equation in terms of the fold changes of z, and then show that the dynamics of the fold change in z is identical for the same fold changes in x. And then we're there. So that's what we need to do. So first we need to define the fold changes. So we have a fold change in x. We have a fold change in y. And we have a fold change in z. Now, okay, so we understand what x0 means. That's a basal level of x from which we change x to a new value. But y0, okay, so that is the steady state of y at x0. And this is the steady state of z at x0. Okay? Okay, so that's what we have to realize, is that we do not know y0 and z0. They are always steady states that are associated with the basal concentration of x0. Then we change x, and then y and z are going to change. And what are going to be their fold changes? Well, this is determined by their current values divided by their starting values. Okay. So let's first write down everything in terms of fold changes, and then it will turn out that we need 1 second. Okay, so y0 is a constant, right? So it's going to be the steady state value of z at x0. So if we divide this by y0 left, but also every term on the right, yeah, then you already see that this becomes d fy dt. So the change in fold, the fold change in y, the time derivative of the fold change in y, and this is going to be equal to fy. So, right, minus fy. Okay, now the only thing what we need to do in this equation is we want to write x in terms of the fold change. So this we can do. So we can multiply it by 1. Right, then x divided by x0 becomes fx, and then x0 remains there. So, oh, there we go. And what we already, so let's also quickly write down again what the steady state was. So ys is beta 1x divided by alpha 1, right? So that means that y0 is that. And we also knew that z0, right, so zs was beta 2 times x ys divided by alpha 2. And then we have to substitute y. Now we achieve this. So this is z0, yeah, and this is y0. Okay, and there we have x0 divided by y0, yeah. Okay, so given this equation, what you see that x0 divided by y0, which appears there, is alpha 1 divided by beta 1, you know. So this equation, x0 divided by y0, we can simplify by exploiting this. Okay, we'll do that in a moment. And the other thing that also the other differential equation we have to write now in fold changes, because now we, as you see, I mean this differential equation that we started with has now been written in terms of fold changes only. Okay. And right, so now the other thing is what we have to do. Okay, we have to divide here by z0, z0 left and right, and then this becomes dfz dt. So this is the rate of change in the fold change of z. And okay, so that's what we need. And then we still need to divide this by x0 and multiply it, so that this becomes fx, right? And we also still have to divide this by y0 and multiply by it. So what do we get? We get beta 2 times x0 times fx divided by y0, z0 and fy. Yeah, I guess that's correct. And the other thing that we need to do still is add this term. Okay, so we know what x0 divided by y0 is. So if we write the first equation again, okay, so we take this guy, we write it in its final format, we see the beta 2 times fx times x0 divided by y0 is alpha 1 divided by beta 1 is minus alpha 1 fy. Okay, so this disappears. So, and the dfz dt still has x0 divided by y0 and z0. So let's figure out what x0, so let's figure out x0, y0, z0, what is that? Well, we know what x0 divided by y0 is. That's that. And then we need to take this guy, oh, I think I made an error here. So, okay, I think I made an error here, so this is beta x, y s, y steady state, what is that? Right, good, that's better. So let me check if it still is. Yeah, that's correct. Okay, so then we need to have 1 over z0, which is basically the inverse of that. So that is alpha 2, beta 1, alpha 1, beta 2. So, hop, 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 hop. It's alpha 2 divided by beta 2. So that means that dfz dt is beta 2 multiplied by that, alpha 2 divided by beta 2 multiplied by fx over fy minus alpha 2 fz. Now here you see that the betas disappear, so the final equations that we are left with are those. Okay. Right, so let's clean the board a bit and look at these equations. What do they tell us? Alright, so what did we do? We defined fold changes, so we said, okay, we're going to start from a basal level of x and change it to a value, a new value of x, which defines the fold change. At x0 we had y0, and when we change x to x0 to x, y will change as function of time, leading to this fold change. The cat wants to come in, so we open the door.